Good afternoon, everyone. Hope you guys are doing very well. The previous lecture we discussed about basic representation for graphs, and we learned about list as well as matrix representation for graphs. In this lecture, we're going to be discussing an important algorithm for graphs. As you know, in our day-to-day life or in general in computing, searching, sorting, these are two major operations. In the graph, what are the ways we can do searching? Okay, if we want to find some element or some node in a graph and we have to traverse the graph, what can we do? So there are two major algorithms come in picture. One is breadth first search, BFS, and second is depth first search. In this lecture, we're going to be discussing about breadth first search, BFS algorithm. Now let's say we have given a graph with some vertices and edges, and this is an undirected graph. So remember, in the similar way we can apply the algorithm on directed graph. But let's say we want to apply breadth first search on this typical graph. Now here we are assuming that this graph is stored as an adjacency list. What does it mean? In the previous lecture, we discussed about what do we mean by adjacency list, that we have all vertices in a list. Say for example, this is a vertex A, this is a vertex S, and what are the nodes connected with A is S, okay, and another node which is connected with A is B, okay. And in the same way, what are the nodes connected with S? A, C, and G. So you can fill it up rest of the list, but just we already learned about list representation in the previous lecture. This is more storage efficient list. So what the algorithm says, let's say we have a starting vertex S. From the vertex S, we want to do a breadth first search. So the idea for breadth first search as it stands that, we want to look all the nodes which are connected with this particular node. Means we are expanding across, or we are expanding in breadth, not going deeper. So breadth means that first we explore all the adjacent nodes, and then after that we go and find adjacent nodes of the next vertex connected in the list. Okay, so that's exploring one vertex and all connections of that vertex in one loop or one time. Okay, so it's like think about say yourself, okay, and you have two arms, right? So you are saying it's an analogy that if you expand your both arms, what are connected to your both arms? Okay. So expanding across or in the breadth. So let's say what algorithm says that for each vertex, okay, so we color. The color is nothing but indicating that did we explore that particular vertex or not. If the color is white, it means that we didn't explore it yet. If color is gray, means we have partially explored that vertex. And if color is black, it means we have fully explored that vertex. Okay. So this is some initialization steps from 1 to say 4, some basic properties, say color, and then D is nothing but it denotes a distance or how much uh, level across that particular vertex is from the source vertex, okay, or some sort of distance, you may say, or level, or how deeper, either way. So that is denoted by u dot d. So initially we say that infinite distance means some very large or unknown negative number, whatever it means, indicating that we don't know yet how much far away that vertex A, for example, is from S, okay. And the predecessor means that who is the previous node or predecessor of this vertex U, okay. So we do some kind of basic initialization, and then since we are starting with vertex S, we color that vertex to gray because we haven't fully explored, we have partially explored that. Now we are visiting that vertex S, and we set S dot D to 0 if it is a starting vertex, S dot predecessor is nil, and also we maintain a queue. So that's an important aspect of this algorithm that has overhead of storage too. So queue maintains, it's a first in first out, queue maintains a list of vertices, which stores a list of vertices which are getting explored on the way, okay. So we need to maintain this queue in order for this algorithm to work. So that's a sort of extra overhead or a storage overhead, you may say, for this algorithm, okay. And then we enqueue, we put this source vertex in queue, and then the next 11, line number 11 to 18 in a loop basically tells us that whatever vertex we have put in the queue, we have to explore the nodes or vertices which are adjacent to that vertex. So we dequeue, okay, this vertex S from the queue, okay. And now for each vertex which is adjacent to this source vertex, means adjacent to this vertex are A, C, and G, 3 vertex. So we put all these 3 vertex in the queue, okay, and we color these vertex to gray because we haven't fully explored, we have partially explored, and the queue maintains that that okay, we have visited these many vertexes, okay, and we keep on enqueuing all the adjacent vertexes in the queue. Okay. And then finally, when we have finished all the vertex which are adjacent to S, we make S or as a black, means we have fully explored all the branches of this vertex S. Okay. Now this thing, the black, gray, and white, say for example, if a certain vertex is black, it has 2 possibilities. Either it is connected with another gray vertex, or it may be connected with another black vertex. So if it is connected with black vertex, means we have fully explored. Gray vertex means the gray vertex may have a connection to white vertex, okay, means it is not fully explored, partially explored, right. So let's say how this algorithm works. So first step, we just do initialization, okay, as we discussed that from line number 2 to 4, we do some initialization for all vertex, and then because our starting vertex is S, we make it gray, and its S dot D is 0. So this 0 or infinity is just showing the distance, or S dot D. Okay. So say for example, S dot D for A would be 1 because it is 1 level apart or 1 edge apart. Okay, you can also say 1 edge or distance, how far it is from the starting vertex or your whatever vertex you to choose. All right, and we maintain a queue as we just said, and in the queue the first vertex, starting vertex S, would be there, and the bottom of the queue is 0, is just denoting the distance for this vertex, okay, from the source vertex. So let's start this algorithm. What we're gonna do when we are at line number 10, we are in a while loop. So what we did, we dequeued, means we take it out one element from the queue, so which is S. Okay, now for each V, means vertex, which is adjacent to U means here S, because we have just taken it out from the queue, and we apply this procedure. If the color is white, means it is not being explored, then we explore it, we make it gray, and then enqueue that vertex. So as you can see here, that we went to vertex A, and we make it made the vertex A color gray, and we updated its distance. U dot D is equal to U dot D. So the distance of this vertex A would be the distance of its predecessor plus 1. So 0 plus 1 is 1. Okay, and now we have enqueued this vertex A in the queue, right? Now we went back to this for loop at line number 12. So for loop at line number 12 says that for each vertex be adjacent to G. So adjacent to G means adjacent to S. First was A, then the second would be, or before going to second vertex, we also can see that, see, we went from S to A. Okay, if we want to expand or visualize it as a tree. So second would be, say, C, which is adjacent to S. So we went to C, we made its color gray and updated its distance, and you can see we put the C in the queue and its distance is 1. And as you can see, if you see the tree representation, we went S to A and then S to C. Okay. And then we have one more connection, which is from the S, adjacent to S vertex is G. So we applied the same process, we made it gray, vertex G is gray, updated its distance, put it in the queue, and as we can see, the tree representation as well. Now we have no more left the adjacent vertex from S. So we are out of this for loop at line number 12, and we make the color of the vertex S black, means this S is fully visited. Okay. Now we are again at line number 11, that we need to dequeue. Okay, take it off one vertex from this queue. So let's see how it works. So we took it out A. Okay, and now we explored A. What is the adjacent to A is B. Okay, made the color gray, and the distance of the B would be 1, predecessor distance plus 1 means 2, and we put this B in the queue. Okay, 2, and bottom is the distance 2, and you can see the visualization of this in a tree form. So from A we went to the B. Now there is no more adjacent vertex left at A. From the A means that we have fully explored A, so we made its color black, right? Next, we dequeue a vertex from the queue, which is C. Okay, so C. So we dequeue it, and we move to the, we see what are the adjacent vertex from the C. Okay, the adjacent vertexes are D and G. Okay, now here at line number 13 we have condition that if the V dot color is white, means if the adjacent vertex is not explored, means, so G was already explored, so we apply this line number 14 to 17 for the D vertex which was not explored. So we went from C to D, made D gray, and put the D in the queue, right? And so now, good. Now we see we have no more adjacent vertex left from the C, which is not explored. So then we DQ, we make its color C, color of C to black. Now we DQ again, which is G, okay, and we see that from the G we have no more white vertex left. We made it black, so all vertices are visited. And then we DQ, and the vertex was B, and B, there was no adjacent vertex left from the B, so we make its color black. And we DQ, and there was a D, okay. So from the D we have white vertex F, so we apply the same procedure, we make its color gray, updates its distance, which is predecessor distance, that is 2 plus 1, 3, and NQ the F vertex. So we NQ the F vertex, and in a tree representation you can see and visualize as well. Now, okay, we went to the F. Now we see any more adjacent vertex from the D, which is white, that is E. Same way, we made the E gray, update its distance, which is 2 plus 1, 3, put the E in the Q, okay. And now we have no more adjacent vertex, which is white, left from the D, so we make D black, means it is fully visited or explored, okay. In the same process, we DQ vertex F, see if there is any more white vertex which is adjacent to F left. If not, make it black, remove it from the Q, and then same the E. So as you can see that we have done a breadth-first search for this simple graph. Okay. Now think about the applications where this is useful, and also think about the storage requirement. So here we have, say, simply few nodes, but think about if we are developing an algorithm for, say, network optimization, where there are millions of computers connected in the network. So we may have millions of nodes, and if we are maintaining a queue, extra queue for the nodes, we would need extra storage. Okay, so storage requirement, we would have a storage requirement for the adjacency list plus extra requirement for this queue. Okay, that's one overhead, that maintaining extra storage. But the beauty is that say if you want to find a shortest path, then this algorithm can find quickly. So you are exploring all the adjacent vertex from the chosen source vertex. Okay. Also, there may be applications, say one application is finding the shortest path between two nodes. There may be other applications where similar kind of situation or similar kind of thing is needed, where we want to find, let's say, cost optimization between two nodes. Okay. So this breadth-first search is efficient in those applications. Okay. So let's talk about something else, about the complexity. So as you can see, from the line number 1 to 4, actually in this for loop we are doing some basic operations in order for this algorithm to work, which will take in the order of V, that is vertex, that's time. And then in the same way, say NQ and DQ operations, they will take in the order of V, that time. And the beauty is that you are storing in adjacency list. So the condition that you only visit the white vertex makes sure that you are not visiting twice. So you're kind of getting a complexity in the order of edges, okay, for these lines 13 to 17. Okay, so in overall this algorithm will take in the order of v plus e time. Okay, so thank you guys for listening and enjoying lectures on the professor channel. Thank you for subscribing, and those who have not subscribed, please subscribe the professor on YouTube. We appreciate your support and feedback. Thank you. Have a wonderful day.